When you go to do a titration problem, the first thing you're going to do is you're going to cancel the heartbreaker. So here's a problem. What I'm going to do is Na is a heartbreaker, so I cancel that. That's always going to give me my equation. So I'm going to react HF plus OH minus, arrow, I'm going to get water plus F minus. We're going to use something called a Bacam table. What a Bacam table is, it stands for B is before, A stands for added, C stands for change, A stands for after, and M stands for molarity, because in all these problems you're always going to need to put it back into molarity to solve for pH anyway. So then what we're going to do is this. The first step is a Bacam table is dependent on moles. We always get moles in any solution from M times L. So what I'm going to do is I'm going to take the molarity of HF, which is 0.1. I'm going to take that and change that to liters, so I'm going to get 0.05. So 0.05 times 0.1 is going to give me 0.0050 moles of HF. Then I'm going to do the same thing for OH. 15 milliliters, 0.1. So I'm going to go 0.015 times 0.1. I'm going to go 0.0015. Then what I'm going to do is, this is critical, I'm going to compare these two numbers. It tells me where I'm at in the titration. If the before line is larger than my added line, I'm before equivalence, which means you do a Bacam table and then you Hasselhoff it. So at this point, since this number is larger than this number, I know I'm before equivalence. My change line is always going to be whichever one of these numbers is smaller. So in this case, 0.0015 is smaller, so I'm going to go 0.0015 minus 0.0015 plus 0.0015. Then what I'm ultimately going to get is 0 for this. This is going to be 0.005, 0.015. This is going to be 0.0035. Now, to get to molarity, because I have the moles after, molarity is always going to be divided by the new volume. I took 50 and added 15 to it. So my new volume is going to be 65. So what I'm going to do is I'm going to divide this by 0.065 liters, 0.065 liters. So what I'm going to do is I'm going to divide those two, which should be like 0.054. Let me see. 0.0035 divided by 0.065 is going to be, 0.054 is my molarity right there. Then when I come over here, I'm going to do the same thing. I'm going to go 0.0015 divided by 0.065, and I'm going to end up with 0.023. At that point, I have, it's like a buffer solution. I have F minus, concentration of that. I have HF, concentration of that. It's time for Hasselhoff. All I'm going to do then is go pH is equal to pKa plus the log of the acid over the salt. So I'm going to go 0.054, 0.023, plug that in my calculator, so when I go to do it, I'm going to take 7.2 times 10 to the negative fourth is going to be 3.14 is going to be my pKa plus, and then I take the log of that. Do me a favor, log that sucker, and then tell me what it comes out to be. And add it to 3.14, whatever it is.
2.77.
Perfect. 2.77, which seems reasonable. We added a base. pH went up from 2.07, so it went up, and there you go. That's how you find pH. That's what you do whenever you're before equivalence. You do a Bacam table. Has to be moles, so we go M times L. Run the Bacam table. You drop it all the way down. You get molarity. You're always going to have, before equivalence, you'll always have some acid and some conjugate base. Throw it in, and you're good to go.